Good morning and good day, everyone. My name is Tony. I'm a course advisor and I will be your host for today's session. Just before we start, I would like to just give some housekeeping rules. So this is the notification and sound settings. So you are able to turn on and off the notification and sound as you wish during this session. And also, please do post any questions under the Q&A function at the top right-hand corner. You'll see there's a Q&A section. You can just post any questions there. If the questions are general questions that has to do with the program offering, I'll be able to assist regarding that. But if they are technical questions, our presenter for the day will be able to then assist regarding that. These are some of the frequently asked questions. So everyone registered for this webinar will receive a copy of the PDF slide and a link to the video recording within the next 2 business days via an email. So please do check your junk folder, spam folder if the email does not appear in your inbox. We will also provide a free digital certificate of attendance for live attendees. So there will be a link and a QR code to a short survey provided at the end of the session. So please do stay with us to qualify for the certificate of attendance. Events conduct. So please keep discussion lawful and respectful. Follow the moderator's directions. Do not share illegal or abusive content. Recording is not permitted unless authorized. Breach may lead to removal and referral under the ECT policy. Just a bit about ECT. So ECTs are affiliated to the well-established Institute of Technology, Engineering Institute of Technology, EIT. Is an engineering specialist. ECT delivers bachelor's and master's program respectively. So our programs are designed by industry experts, ensuring that you graduate with a cutting-edge skill that are valued by employers. And ECT is registered and accredited, meeting the Office of Student Requirement for course quality, academic standard, and student support, also student operation. Our teachers are subject specialists. Our teachers are subject specialists with industry experience and requisite academic qualification. We deliver our programs via a unique delivery methodology that makes use of a live and interactive tutorials, which is also, the classes are also recorded, so you are able to go through the recordings at your own convenience. So today's topic is the basics of power electronics. And the presenter for the day will be Dr. Walid, who is also ECT Programme Leader. Dr. Walid, you can take control of the slides.
Yes, thank you very much, Tony. I'll just take control. Okay, thank you, everybody, for attending this webinar. This is Walid Issa, your host today, the ECT Program Leader for Electrical Engineering, responsible for the undergraduate and postgraduate programs. So if you are interested for online course, undergraduate or postgraduate, please look at the website for electrical engineering and power systems and ask any question maybe at the end of this webinar, or maybe later on using the channels announced on the website. Okay, thanks again. And we are going to start our webinar today about the basics of power electronics. I teach power electronics at different universities, and this topic is kind of very blended with different disciplines, and also it has some aspects of electronics, of control, of power, all of them together in one topic, which is called power electronics. It's not an easy topic to learn for beginners, but it is very important now topic for everybody because of the integration of more renewable energy and electric vehicles. So that's why I I thought about delivering a webinar about it. So now let's start talking about the power electronics and what is power electronics. As I mentioned before, it is two terms here, the power and electronics, and between them is something called control. So, for example, if you have different resources of power, or maybe renewable energy or battery systems, and you want to deliver that power to a load, and that load might be a motor, might be a resistor, a heater in food processing facility, you need to make a compatible power between the source and the load. Maybe the load an AC motor. AC motor needs AC power. So you can't really power it from battery directly. You have to have something called converter. And that converter is made of something called solid state electronics. Solid state means something made of silicon like transistors and diodes. Okay? So you have to make up a converter made of transistors and IGBTs and diodes, and then you have the power at the left-hand side, and you will get output power that should suit your load. But to make sure that suits our load, we have to have a controller unit here. That controller gets a feedback and send the proper control signals to the transistor to turn on and off. Just want to confirm, Tony, do you see my pointer while I'm pointing?
Yes, I can see. Yes, I can see your pointer, Doctor.
Okay, that's good. Thank you. Okay, so that's the power electronics. And what does power electronics really do? They are provide efficient and flexible control of and conversion of electrical energy. As I mentioned before, you have, for example, battery system, but you need to supply a different level of voltage or maybe different type of voltage like AC. You have to have a conversion. That kind of flexibility can't be offered by different disciplines, mechanical, for example, or relay using relays. No, you have to use solid state converters. So the first type of conversion that you might already studied, if you are interested in power electronics, you should have at least a background about maybe electrical, electronics. You know, the first thing that we studied in our degrees is the conversion from AC to DC. AC means alternating current, which you got from your outlet at home. And DC is the direct current, which, for example, something is necessary and used by our laptops, internal circuit of laptops, internal circuits of mobile, maybe some of the modern appliances, for example, like maybe washing machine. You have some DC sources have to be supplied there, and other systems. When you charge your electric vehicle as well, you have to have DC, not AC. I mean internally. So that AC because it's already our supply, and that's DC because we have different loads like heaters, lamps, and DC motors. And that process is called rectification. Now, sometimes you have DC sources. For example, you have DC batteries. You have power from PV, photovoltaic solar system. It's already DC. Or maybe fuel cell that converts hydrogen to electricity. That's also provided DC. So you have DC power, but you need to convert it to another level of DC. Why? For example, your phone needs 5 volt to be charged, for example. So you need to use a battery from your vehicle that provides a 12 volt, but you have to step down that voltage from 12 to 5 to suit what? To suit different loads like electronic circuits and maybe different machines. Sometimes you have DC sources, but you need to convert it back to AC. For example, you have a battery system in your vehicle, but that battery system, DC, you need to supply power. You need to convert it to supply an AC motor that drives the wheels. So we have from DC to AC, and that is called inversion, DC to AC. And that's because we have machines that require AC, or you want, for example, to sell power. For example, getting power from solar systems, it's DC. But to sell it, you have to convert it to AC, to sell it to the grid, because the grid is AC. So you have also another conversion process here from DC to AC is called inversion. And the last one is from AC to AC. And AC to AC conversion happens because, for example, if you have two countries, and these two countries, you want to couple them. You want, for example, to make like a connection between these two countries. But these two countries, for example, they have different frequency. One is 50 hertz, one is 60 hertz. You can't connect them directly. You can't synchronize. You have to have what? You have to have conversion from AC to DC and then from DC to AC. That's one of the applications. Another application is maybe it's at your home now. You have a dimmer circuit. Dimmer, that you control the light intensity. Okay, it takes AC from the grid, but it converts it to a chopped AC. So still AC. It didn't convert it to DC. So conversion from AC to AC also happens in the dimmer circuit to give you a flexibility to control the illumination of your light at home. Now, other applications for power electronics everywhere, literally. So we have, for example, converter units or board units for elevators and escalators, for motor control in our factories to control the conveyor speed, for induction heating in factories, for cooking equipment. You have electric cooker, for example, at your home. How you control the amount of heat and energy that delivered to the heater is by a power electronics converter. In air conditioning unit, refrigerators, and also the personal equipments and mobile and other things. You have also aerospace applications where you need to supply power for different sectors of, for example, the plane or aircraft. They need different voltages. Telecommunication, where the tower is far away from the grid, you have to rely on battery and solar system and make some converter to merge these power together and provide to the amplifiers there and telecommunication systems. Or transportation, when you have electric vehicles, you have electric bus, you have trams, all of them electric. They need to manage the charging and discharging, and also conversion to drive the wheels as well. All that is application of power electronics. So it can't be done by just electronics. It can't be done by embedded system only. It can't be done by relays and contactors. It can't be run by control me people only. It is everybody. All expertise together will merge in one topic called power electronics. When you look at the market is now booming for power electronics, and for obvious reasons. The first one is, the climate change, and many conferences have been held by different big countries in Europe, in UK, and America as well, and Middle East. They want to reduce the emission from carbon dioxide. They want to minimize that emission because of the climate change that happened. And to take action of this, you have to electrify your system, converting them from using coal and fossil fuels to use renewable energy systems. And that's why the investments into power electronics was booming, and still now a lot of people are required to be hired in companies, and also a lot of investments from governments already put to encourage people doing more products to meet their plans about net zero. Every country has a net zero plan to reduce their emission and to integrate more renewable energy stuff and to electrify their systems and their power systems as well. So in 2023, about 26.5 billion is the market for power electronics. And that's not just for converters. It is for material. Maybe they don't need to stick with silicon. They are now seeking, is there another material that can be used instead of silicon, and how good it is, and also in converter level. And now in 2030, the expectation is to invest $37 billion. Okay, and maybe the UK is one of the major players in this because it has manufacturing for power devices. Power devices means MOSFETs and IGBTs, and it has a lot of companies producing converters as well. So there's a lot of investment, and that a lot of investment also encourage people to go into that discipline to get a job. The investments, again, has been maybe divided into different categories. Some of them are, maybe the majority of that fund is already going to automotive, and we know electric vehicle now is moving forward. More countries deploying chargers and encouraging people to own an electric vehicle instead of fossil fuel or petrol or gas vehicles, and that's why the biggest investments in that area is big, followed by industrial, where they electrify their systems, the conveyors, the motors, the heaters, everything in these factories also, or maybe industries, they also electrify it, and maybe followed by some other investments into the telecommunication part, in medical part, and consumer unit part as well. That happened in 2024, and it's a copy-paste version of that with bigger budget. It will be happening in 2030. Okay, so from there, you know, okay, the most maybe a fund will go to the automotive sector and also the industrial sector. Again, about the jobs and markets, I think maybe the picture here is blurred a little bit because it's small, but I think you can do the practice yourself. Go to LinkedIn. I think all of you should have LinkedIn profile now. Go to LinkedIn and look at power electronics engineer and see how much really you earn. So this one is saying here £60,000 a year, which is good income for a starter engineer and for mid-range, mid-career engineer. £60,000. And let's look at what they require. They need somebody expert in inverters and DC converters, which is covered by power electronics curriculums. They need somebody to know MATLAB and BSIM and the Plex. So from there, we learn what the skill set and softwares they need for this industry to be recruited by them. And also they want you to know silicon. Yes, they are used for manufacturing MOSFETs and transistors, but there are other materials like silicon carbide and gallium nitride. You should be aware about it. We are not material chemistry people. We are electrical people. So we should know at least the properties and from where we can buy them and what is the advantage of using them. Another job descriptor is about £75,000. And it says again here, you need to know about silicon carbide, and gallium nitride. You might maybe questioned in the interview about these. You need to know softwares like, for example, LT-Spice. LT-Spice, I used it before and I use it in my teaching as well. It is free software, very capable, very flexible. A lot of tutorial on YouTube about LT-Spice and how you use it for simulation as well. So it's good to know it from now after this lecture. Why not you go and type these keywords on YouTube and see what it goes, okay? And use ChatGPT to discuss. Please explain to me what's the difference between silicon carbide, and GaN. If I have interview and I've been asked about this, how to answer. This is the thing. This is the thing I want from this webinar. I want you to know what is expected and how to deal with this later on. Maybe some of the attendees, which I don't know, maybe very expert in power electronics and they just attending for curiosity. But I think the majority of people here are driven by, I want to know what it is, or I'm interested, I want to know what is the plan for or pathway to go for a job. You have to know softwares like Plex, MATLAB, Simulink, Altium, KiCad, and also to know about converters and gate drivers design. Okay, let's now go back to the topic, why power electronics? Okay, we explained power electronics is for a lot of things, but let's now ask a question. We know now the cycle from fossil fuel energy to get power to the load is going through, for example, burning the coal, that is 100% energy there is conserved, but you burn it and convert it to chemical energy and then thermal energy to get fuel out of it, you have some losses, which is about 65%. Then you convert it to thermal energy and you boil some water to convert it to steam, and then send that steam to turbine called the steam turbine. And the efficiency of the steam turbine is about 35%. So more than 65% is wasted. And then that turbine is now generating mechanical energy. It's coupled with electrical energy. That electrical energy conversion might also have some losses. Finally, it will end up with 16.5% to the load, to customer, to me and you. So 100% energy was already in that coal, in that fossil fuel, is already 16% is just obtained and given to you. And the other part are losses. See how much losses we have in this system. But the question now, okay, we are using a lot of fossil fuels to generate a little bit of energy for us. The conversion loss is high. So how long will it last? The fossil fuel best for example, expectation about the time is about 150 years. Maybe if we use it at the same rate we're using it now, it will save us for 150 years. Okay, we might all not be here after 150 years, but what about our kids, our next generation? Do we need to be selfish, or we think about them? So we have decided to think about them. That's why we have power electronics, to integrate more renewable energy, to make the world better and more efficient. Why? Because if we reduce the fossil fuel, we can replace it with another energy systems, and that fossil fuel can last not for 150 years, maybe another, maybe 300, 400, 500 years as well, because you have reduced the consumption of that fossil fuel. What happened after 150 years, we don't know. It depends on our habit. But let's do an action now. So we can extend the period by using it efficiently, by improving the, even if you use it efficiently, we still have the global warming problem. Improving the efficiency conversion and promote more integrated renewable energy, and that's the role of what? Of power electronics engineers. Now, let's have this example just to focus on something. We have 100 kilowatt, for example, as cool. But as I mentioned, we converted them to 16.5% here. That means that the percentage is 6-1. For example, every 6 maybe kilowatt stored energy in fossil fuel, you just get 1 kilowatt as output. Okay, so the question now, why, if there is a very high conversion losses here, why do we spend efforts on the load side? Load side is this one. Okay, why we say let's increase the efficiency of electric vehicle charger? Why we say let's increase the efficiency of our lamps instead of the old lamps, tungsten lamp, we use LED lamps? Why we focus on converting our refrigerators, microwave, fridge to be, for example, more efficient? The losses is not here, the losses is there. Why? Because if you look back, any 1 kilowatt saving you do, for example, your electric vehicle was wasting, for example, 2 kilowatt hour, okay, or 2 kilowatt, and just talk about power, not energy, 2 kilowatt, for example, and you have done something to minimize that losses to 1 kilowatt hour, for example, you will get saving back about 6 times. Okay, so it's worth really doing some savings here, because when you reflect it back to the source, it will be 6 times saving more. Okay, when you do here 1 kilowatt saving, still not too much, it's still 1 kilowatt saving. Okay, but here when you do 1 kilowatt saving, it will be reflected back as 6 kilowatt saving. That means I will use less fossil fuel and make more efficient system and make it extend lifetime for longer. So that's why it's very necessary to work on the drivers, work on chargers, work on power converter efficiencies, and that's done by what? By power electronics engineers. Let's have an example, guys. We have converter, and we know the converter has power input and power output, and we have losses. why losses happen, I will ask a question. If you have a laptop, and after 1 hour, for example, of working on that laptop, if you can touch your laptop charger, what do you feel? You feel it's hot or warm. It depends. Why it's hot? Because it has power input and it spits out power output to your laptop to charge the battery of your laptop. But through this conversion, there are some resistors there, there's some power converters and MOSFETs, and all of them, they dissipate power. How they dissipate power or losses? As heat. So the heat is a sign of power losses, okay? So that power losses, it will be emitted whatever you do. You don't have an ideal system, 100% efficiency. You might have 90% efficiency. That means 10% will be losses. Now, from this equation, from this graph here, we know that what is the efficiency definition? Definition is power out divided by power in. And we know the power input is divided into power output and subtracted from and add to that the losses, okay? So the power input is the power output plus the losses, okay? If I take that power input into the equation here, I will get this in. And if I make a cross multiplication, I will get this one. And if I made the power out, I take power out from here, power out from here on one side, I will get this equation here. It's a very simple equation, but we will learn a lot from it. Power output here equals efficiency divided by 1 minus efficiency multiplied by power loss. Where is power input here? Power input has disappeared. Okay, we don't want to understand, we don't want to have power input now contribution. We don't need it now. We want to understand how much is the efficiency or power losses impact on our power output. Let's have an example. If you are engineer and one company giving you power converter number 1 with efficiency of 85%, another competitor give you a converter number 2 with efficiency of 95%. What do you think? Now you have 85% with, for example, it costs £100, but this one costs £200. Will you buy the first one or you will buy the second one? There is an efficiency difference here about 10%. Does it worth to pay double the price? That's the question. If you are starting engineer, you might say, okay, 10% more is not really worthy to pay double the price. But let's do the assessment now. The assessment is, I want to get output power from the converter 1 and output power from the converter 2 to make losses here 1 kilowatt, 1 kilowatt. So I will keep drawing output power until it reach power losses here of 1 kilowatt. The same will be done here as well. So what we have here, we have the same scenario for both of them. I consumed output power until the power loss reached the maximum of 1 kilowatt, and they are now at physical constraint of 1 kilowatt. What is the power output here? Let's use this equation. 85%, 1 minus 85%, multiplied by 1 kilowatt, which is the loss here. How much I get? 5.7 kilowatt. 5.7 kilowatt is a good amount. I can use it for charging my electric vehicle over the night, and it might charge my vehicle in a few hours. Okay? What about the second one? Is it just 10% more? Let's check. When we do the calculation, it is 19 kilowatt, 3 times more. 3 times more means I can charge my electric vehicle in third of the time. Third of the time. I can charge another electric vehicle over the night and another electric vehicle, because each one will get third of the time. So I can make a faster charging by just 10% more efficiency. Okay? That's the beauty of efficiency here. 10% more give me 3 times power. Does it worth paying double the price? You say it. Okay? Or it opens for me another opportunity here. Instead of charging one electric vehicle, why I don't sell it as 3 output electric vehicle charger? One for your electric vehicle and one for another 2 member of family electric vehicles, or maybe in the business itself you have members of staff. electric vehicles. You can just buy one converter with 3 outputs, and it can deliver power for 3 cars. That's because of 10% more efficiency. I want you just to appreciate and increase the awareness about the efficiency. That's why a lot of companies compete with each other. We want to increase by a fraction of efficiency compared with other competitors. Why? Because it's worth a lot. And you see the evidence now. So high efficiency, that's second question now. Okay, we appreciate now efficiency. How we increase the efficiency? We increase the efficiency by using good switches. When I say switches, diodes, transistors, thyristors. Maybe for transistors, they are made of silicon before, for decades and decades, but nowadays they are made of silicon carbide, and GaN. You have to make a good selection, and maybe you change. If you are doing power electronics design, you might say, I don't want to stick with silicon. I will see if I can use silicon carbide or GaN. That will reduce the losses and increase the efficiency. Or you should be aware about more topologies. I mean topologies to increase the efficiency, like interleaving, switch capacitor, maybe hardware or soft switching, hard or soft switching techniques. So what I need to study power electronics, because the power electronics modules curriculum, they give me awareness and knowledge about what switch is there, what features, how I select, and also what topology is there and how I select. Okay. So now the question about power devices. How we know the power devices? You have to study diodes, different types of diodes, general purpose, high-speed diodes, and Schottky diodes, the difference between them. That will enable you, for example, in interview, when they ask about, okay, you have a converter, what diode do you need to select? You have to tell them, okay, we have different types of diodes, the features of 1, 2, 3, and based on the voltage level, based on the current level, I can select that one for that reason or that one for that reason. Power switches like transistor, you have BGT or MOSFET and IGBT. In power electronics, we don't use BGT. We use MOSFETs or IGBT. And the last one is, can I just check? Some attendants said we can't see the slide. Can they? Do you see slides, guys? Just to check.
Yeah, can everyone confirm if they can see slides? I can see slides on my side.
Okay. So maybe it's just a few people to log in again.
Yeah, it's probably
if you can't see
people.
the slides, please log out and log in again. Maybe you can see it. But we have confirmation from other people that they can see the slides and can see me as well. Thank you very much for your confirmation, guys. Okay, let's now continue. So to know more power electronics, you have to know more about power transistors and power thyristors as well. So that's the devices or switches. What about topologies? When you look at this slide here, we have 4 different topologies. Okay, and each one has a purpose, maybe step up or step down conversion. Okay, but look at them. They need a switch like MOSFET, a switch like diode. They need also a couple of, for example, capacitors and inductors. The same is here as well: inductor, capacitor, MOSFET, and diode. This one is a step down converter. This one is a step up converter. And this one is a flyback converter, which is the one that's used in your laptop charger and your iPhone charger, smartphone charger. It is this one, okay? Because it has transformer, and transformer provide isolation, and isolation is a requirement for consumer equipments. And this one is a different one with the larger transformer. So different topologies have different properties and different also safety features. So more knowledge about them by studying them make you more power electronics engineer. What about electric vehicles? When you look at electric vehicle, it has a lot of power electronics converters there. You have battery, which is DC, but you have also a motor, which is AC to drive your wheels. How we make compatibility between them? We have to convert the DC to AC by using what? By using the inverter. But unfortunately, the inverter sometimes they need higher input voltage here. So I can't take that battery voltage, which may be 200 volt, to supply the inverter. The inverter needs 700 volts. So I have to have step-up converter, which is boost converter here. That boost converter can boost that voltage to here and then convert it to AC. That's something that can be found in electric vehicles. Now let's talk about PWM. PWM is very essential knowledge in converters. Okay, you can't make any converter, power electronics converter, without knowing what's PWM. And to just understand what's PWM, you have a motor and you have a battery. You want to supply that motor with that battery, you just wire it like this. And when you wire it like this, the motor will go to the top speed directly. What if I want to control that speed? I can put a resistor there. That resistor, I can increase the resistance, decrease the resistance to make what? To make the current flow more or low. And that will make the speed higher or lower. But let's assume these values, 1 kilowatt ohm here and 100 milliampere here. What is the power losses? Power losses equation says I square, which is the current squared multiplied by the resistance. The current square multiplied by the resistance is about 10 watt here. 10 watt is not big, and yes, you can find in the market a 10 watt resistor, maybe half of your finger, which is okay. What about I have different motor here? That motor, for example, or different motor that requires higher current here. Okay, so that higher current maybe it's 1 ampere, so it's not a toy current, a toy motor. It's maybe more industrial motor. It needs 1 ampere, and I reduced also the resistance to 100 ohm. Why? Because of the high ampere here, I have to reduce the resistor. What about the power loss? Power loss is 1 ampere square multiplied by 100 ohm. That's 100 watt. 100 watt is massive. You have to have a resistor maybe the size of your hand, okay, which is very big. What is the solution? Okay, let's replace the resistor with something called the transistor. Transistor, what is called the transistor? Resistor is from resistor and tran from transfer, variable, okay? Transfer transistor. So that means I can have a variable resistor, but using something called the transistor. The transistor, I can supply a current here, and I can get a different current here, okay? I can make that transistor to be like a variable resistor. And it's small, much smaller than my hand, that variable resistor can do. So I can use that transistor to behave like a variable resistor, and I can control it using a current onto the terminal called the base. Okay, this is called linear operation. And in linear operation, for example, you have a relation between the amount of current you push into the base and the voltage that is applied into the load and the transistor. If you have 0 ampere going into that transistor, that will make the transistor turned off. And when the transistor turned off now, what is the voltage between that terminal of the transistor and that terminal of the transistor? It will be about 100 volt. Why? There is no current here. So this 100 volt will go down, down, down. Nothing is dropped here because there is no current, and will go down and appear here. So the point here will be 100 volt, and the point here is 0. 100 minus 0, it will be 100. What about if I pushed a lot of current? If I pushed a lot of current here, that transistor will behave like a wire, a short circuit. And if it's short circuit here, the voltage drop here will be 0. So between this point and between this point, I have something called the load line, okay? And I can, for example, choose to check also the power on voltage on the load. If the voltage here is changing down, the voltage here will be changing up. The summation between the load is here, is my heater, is my motor. The load voltage will be increasing if I decreased the transistor voltage, and reverse versa will happen as well. But what about the losses? Let's, for example, I choose an IP here. I pushed a little bit of current into the base. to make the voltage across my load about 50 volt. Now, I have here 50 volt across my load. From where? From my IB control. I change the IB to make 50 volt here. So how much current in my load? 50 volt divided by 5, it will be 10 ampere. So, okay, I know 10 ampere here. 10 ampere will go through my load and will go through my transistor. If my transistor now has 10 ampere inside it and the voltage across it is 50 volt, how much power losses my transistor will have? 500 watt. 500 watt is boiling my transistor, will kill it in seconds. Okay, so that's why what they do, usually they make transistors in parallel. They make 10 or 20 in parallel just to handle that amount of power. Okay, but the bad point is not this. The bad point is I am sending to my load 500 watt, but at the same time my transistor also wasting 500 watt. So that waste is my problem. I don't want to waste that much of time, of money and power. Okay, so the amount of power here lost is my problem. So yes, the transistor can do the job. It can make control. It's better than transistor, the resistor. It might be smaller solution, but still wasting a lot of power, and that's my problem. The efficiency is just 50%. I wanted to push it to 90%. How we do that? Using PWM. PWM means you can give power to my motor as a constant voltage or as a zero voltage, but at the same time I can chop it. Chop it means I can turn on my motor for few milliseconds and turn it off for a few milli or microseconds. It depends on the frequency, and that's called now the square wave, and it is the PWM. PWM means pulse width modulation. Okay, so what's the benefit now? Pulse width modulation, now you can control how long is your turn on and turn off. You can say, I want to turn it on for 10 microseconds and turn it off for 10 microseconds, or turn it on for 2 microseconds and turn it off for 8 microseconds. The amount of turn on and turn off will determine what? The average voltage that goes to your motor. And if the average voltage is high, your speed will be high. If average voltage is low, your speed will be low. So what's PWM? Again, PWM can be 50-50, and we have average voltage is 50%. So for example, this is 9 volt. If I use PWM to cut that, for example, if you have 9 volt here, if that PWM used to cut 50-50 of that 9 volt, it will arrive here 4.5 volt. What about different version? Maybe 10% here or 80% here. Okay. What we call this percentage, we call it the duty cycle. We call it the duty cycle. So the duty cycle is what? Is the turn on time as a portion of the total time. Turn on time is 50%. Turn on time is 10%. Turn on time is 80%. So that's the duty cycle. And by changing the turn on time, you can deliver higher or lower voltage to your load with no pain. But what about the losses? That's the second question. In the left-hand side, we investigated that as 500 power loss, which is a huge. And why it happened? Because when you multiply the voltage across your transistor multiplied by the current in your transistor, power is what? Voltage times current. You have voltage here and you have current here. Multiply these together, it will tell you what's the power loss. And again, I said in the beginning, power loss will be converted as heat, and heat means boiling, and it might kill the device. What about the switching operation? Switching operation, when I use PWM now. PWM, you make the transistor turn on completely, so here, or turn off completely, so it's here. It's not in the middle. It's not in the middle at all. You turn on the transistor, so it will be here, or you turn off the transistor, it will be at this point. Okay? What if I want 50 volt? What I should do? If I am here, it will be 0 volt. If I'm here, it will be 100 volt. To make 50 volt, you have to tune your PWM to make a duty cycle of 50-50, 50% duty cycle. So if I applied 50% duty cycle here, I will get 50% of the voltage here and 50% of the voltage here, okay? Which is good for the load. The load needs 50 volt, that's okay. But what's happening to the transistor? Let's see. The transistor, if I turned on the transistor, what will happen? It will behave like a wire, okay? A wire here means the voltage across the transistor is 0. And whatever current coming here, anything multiplied by 0, it will be 0. So if I turn on my transistor, it will not dissipate any power. It will not make any heat. If I turned off my transistor, I completely remove the signal from here, it will be off. Is there any current will go there? No current will go into my transistor, and also it will be 0 current. Multiplied by any value, it will be 0. So if I turn it on, it will not dissipate any heat. If I turn it off, it will not dissipate any heat. So in general, it will be 0 watt dissipation, completely lossless, okay? Which is a good thing. This is ideal word. In practical, it will dissipate a little bit, maybe a few watts, but not massive, like 500 watt. So now let's talk about power switches very quickly before we finish. Power switches, one of them is the diode, and the diode is a solid state switch, turns on by itself if the anode terminal, we have anode terminal and cathode terminal, if the anode terminal has higher voltage than the cathode. Another power switch is called the transistors and thyristors. The transistors, they have a third terminal. So this one is BJT transistor, cathode and collector and emitter. And this one is a MOSFET, which is commonly used in power electronics, drain and source and gate. I have base, I have gate. If I give current or voltage here, it will make a channel for the current to go from top to bottom. That is fully controlled one, because I can turn the current off or I can turn it on. But what about thyristor? Thyristor, if you heard about this device before, I can turn it on, but I can't turn it off myself. I can give a signal here. The anode will conduct current to cathode, but I can't turn it off. I have to make some other conditions to turn it off. This is called semi-control. But again, if you have a switch, you can turn it on. It ideally, it should give you any current, infinity to minus infinity, and the voltage should be 0. If you turn it off, it should handle any voltage, positive or negative, and the current should be 0. Does that happen in real life? No, this is ideal switch. And during the transition from off to on to off, there is no transition here, so the power will be 0 as we calculated before. The power losses will be 0. So in ideal switches, there is no heat dissipation, no losses, and we are happy. But unfortunately, we don't have this. Okay, before we jump to the next slide, it's good to point here. This one here, from on to off or off to on, we have something called the switching losses. And this one here is called conduction losses. They are all 0 because we are having ideal switch. What about practical switch, like transistor, like diode? What we have? We have voltage drop and current as well. We have voltage drop across all switches during the on and off time. And when you transition from off to on, you can't make it instantaneous. You have to have time, because there's physics there, physics. The physics tells me that you have time to make the transition from on to off. You can't make it instantaneous. During that time from off to on and on to off, my current rising, my voltage falling, and that will make them dissipate some power, and that power will be like this. So this one is the switching losses, and this one is another switching losses, and this in the middle is called conduction losses. So switching losses during rise up, switching losses during rise down or fall down, and you have in the middle here something called conduction. It's already conducting, but it's losing also power. So that's the practical switches here, and we have power loss, which are merging between switching losses and conduction losses. All these calculations and benefits are also learned from power electronics modules. And this is slide showing as well, again, what is the reason about why there is a slower or not instantaneous transition between off to on and on to off, because we have charges, we have electrons between the silicon types, N type and P type. We have electrons. If you want to turn on, you have to deplete that electrons. If you want to turn it off, you have to charge that electrons. During charging and discharging, it needs time, and that time will be like this. Okay, that's again physics level. We don't want to discuss that point. Now, is there one type of diodes? No, you have different type of diodes. Power diodes, they can be signal diodes or power diodes. What is signal diode? Signal diode is just p-n junction. I think everybody has studied that before, but they can just handle low power and low voltage. What about power diode? They have made a thicker inner area here of N-type, okay? And that thicker area will make it handle more current and more power, but at the same time, they are dropping higher voltage. Again, when you look at the power diode, yes, they can turn on if the anode voltage is higher than the cathode voltage, but at the same time, you can't turn off quickly. During turn off, the orange trace is what I want, but unfortunately, this doesn't happen. What's happening is the current will go and pass and conducted from cathode to anode for a very short time, and during that short time, my diode might dissipate losses and heat. Again, this is called reverse recovery time. And you have to also, for example, you have to know about the properties of diodes, for example, which one is fast, which one has higher or lower recovery time, and which one is better for your application. And these are some small comparison because we have three types of diodes: general diode, fast recovery diode, and Schottky diode. Fast recovery diode is the best for everything, okay, but it might not really be useful for every application. Schottky diode is good in fast recovery diode, fast recovery time. It doesn't have any recovery time, but unfortunately, I can't use it for any application over than 100 volt or 200 volt. I can't use it for application 400 volt or 1000 volt. Which one I can use? Fast recovery diode. Okay, so you have to make a small self-learning activity to know and to ask these questions. And I'm now telling you about the questions, what to ask ChatGPT, for example. And then you ask them about what is the difference between silicon carbide, and GaN, why they are good for power electronics devices. For example, silicon carbide, they have thermal conductivity about 4 times or 3 times more than the silicon. What that means? When they dissipate heat, they don't trap the heat inside. They release it to outside easier than silicon. That means they can make harsh environment availability, and the heat sink and the fan requirement will be less. Okay, so that's the a good thing about silicon carbide. So this image here is showing how many applications there are in the silicon, or silicon serving them. And now silicon carbide is like conquering the market and taking more of the application for its own side. But gallium nitride is still working in high frequency but lower power. They can't serve for high voltages and higher power so far. But maybe in the coming decade, different material, different properties might booming, and surprises will happen. So I finished my presentation now. I hope at least I give you some keywords to take out from this presentation. And if you have any question, please feel free to ask in the QA section.
Thank you. Thank you very much. Thank you very much, Dr. Walid. That was a very informative session, and I hope the attendees also took the same sentiments as me, or take the same sentiments as me. So yeah, we are almost at the end of the session. So let me just quickly check. So on the screen, these are some of the upcoming programs at ECT. As you can see, on the right-hand side is the course names of the programs are the bachelor's and master's respectively, and the start date on the right hand side for this year and next year. So for more information, you can just check our website, and our course advisor will then reach out to you if you have any other questions. And so we also offer professional certificate. There's a 3 months non-accredited professional certificate that is delivered by ECT affiliated institute, EIT, Engineering Institute of Technology. So what it is basically, it's if you want to upskill yourself in a certain area within the engineering space, you can do the professional certificate. And another thing is that we are running a promotion. So for a limited time, you can save up to 334 pounds on our 3 months online professional certificate delivered by EIT. So you'll need to enroll by 30 November 2026 and pay only 599 pounds, 599 pounds for the the usual amount is 933 pounds, 933 pounds. So I'm gonna be sharing the link now to claim the promotion. I'll share it now on the chat box. So you have to register before 30 November this year to get the promotion prices. So I'm gonna share it now on the chat. I've shared it now. There it is. So on the screen now, this is the QR code. So you can scan your phone here to claim the certificate of attendance. So please do note that the link, or the link, yes, does expire after 40. So you have to claim the certificate within the 48 hours. So I'm going to be sharing the link also to the certificate, but you can scan the QR code on your with your phone. So let me just quickly share the link also. There's the link that I've shared on the chat. So you can just claim the certificate of attendance. Just to reiterate, 48 hours it expires. After 48 hours, it does expire. So please, and there hasn't been any questions. Let me just quickly check if I can find any questions. There hasn't been any questions from our attendees. So I'm assuming everything was clear that was delivered by Dr. Walid. Let me just see. Oh,
I've seen a
yes.
question.
There's a question. Let me see.
Yeah, there a question as a reply on the first question, first note in the QA. Yeah, okay. The question is, which type of power electronics topology in electric vehicle? I think the electric vehicle chargers and they deploy, or converters, they deploy something called dual active bridge. Dual active bridge, they use transformer to provide isolation, and that also provide high power. They can use different topologies, but this is the most common one they used it. So it's called dual active bridge converter. Okay, I hope I answered the question. I don't see there are other questions there. So thank you very much, guys.
Yeah, thank you very much, Dr. Walid, for this amazing presentation, and thanks to our attendees for taking their time attending this session. I hope it will definitely impact your life in some way or the other. So that's it. Any last words from you, Dr. Walid?
No, thank you. I encourage everybody just to get some keywords and checkouts and go to ChatGPT, go to Google, go to YouTube, and start asking some of the questions that you don't know, and learn by self-learning what are these. And I think if you get interested in power electronics, you will enjoy it, hopefully.
All right. Thank you once more, Dr. Walid, and thanks once more to our attendees. We will see you on the next one. You guys have a great day ahead. Bye for now.
Tony, if you can stop the recording as well.
Stopped it.